SwayamPrabha. Digital India. Educated India.
Welcome viewers to the 18th lecture of the course Metal Cutting and Machine Tools. In this lecture, we will try to cover gear cutting, computer numerical control and non-traditional machining methods. Though I have a feeling that the last part of our discussion might be spilling over, because the extent of the first two by themselves, it will be quite quite time taking. So, let us move on right away to gear cutting methods. You will notice that we have already discussed something about gear cutting in case of milling machines. Okay. In milling machines, we have discussed forming methods, that means where the shape of the cutter is a conjugate or opposite of the job shape, and that is what we have done in milling. So, I will just jot down those notes. Here we have discussed about simple indexing, which comes in handy during milling. Simple indexing. We have discussed about differential indexing, all very relevant to gear cutting, and we have also discussed something about helical milling. So, which will allow us to cut helical teeth. We have not carried out any calculations on helical teeth. Okay. I will quickly within 5 minutes or so, I will try to discuss what are the calculations involved in helical milling. So, if you remember, in helical milling, we had a figure in which we extensively discussed that the rotational motion of the lead screw has to be related to the rotational motion of the workpiece. Why? Because if we are cutting a helix, then the rotational motion involved in making the helix and the straight line motion in climbing along the helix, they need to be related. Okay. So, if they need to be related, what was the rotational motion coming from? The rotational motion was coming from the rotation of the job, and this was the figure like. So, this was the figure like. I will draw the simplest possible description. This was the lead screw. Okay. It was at an angle. So, if we had the lead screw, it must have been travelling on a nut which had a pitch. So, let us say this pitch is equal to say P or say 5 millimeters. So, if the lead screw has a pitch of 5 millimeters per rotation, it will make the table travel. So, this is the table. The table will be travelling per rotation by a distance of 5 millimeters. Okay. And what did we do after that? We connected a gearbox here. So, let that gearbox ratio be U. That is fine. So, if U is the gearbox ratio, it was ultimately giving its output. Okay. Let us call it NO, output, to the indexing head, and in the indexing head, it undergoes a change in rotation, and it ultimately it is giving that rotation to the workpiece. So, this one holds the workpiece. Let me put a different color. This is the workpiece. So, screw rotates, table moves, gear ratio changes this RPM and gives it to the indexing head. This is indexing head, I head. So, we will write this down so that we do not forget. So, it is lead screw, to the gearbox, to the indexing head, and then on to the workpiece. Achha. How much rotation, how much straight line motion should take place, linear motion, how much should be the linear motion by the time that the workpiece rotates once? That we need to find out, and we can apply it in this particular relation, and that will give us a helical cut. Okay. So, let us quickly have a look. First of all, if this be the gear, these are the helices. As many teeth as you have, so many helices. So, it is a multi-start threaded element, but we take only a slice of that, and this is our gear. So, if we unwrap this helix, if we unwrap a single helix, it would look like this. This is it, where if we are unwrapping it, this must be pi d. So, this is pi d, and this is given a name lead. You must have you noticed that we were saying the multiple start threads. If we move like this, distance between similar successive points will be equal to lead, and this is alpha, and this is given to us. If it is not given, it can be calculated from the other values. Okay. So, how much is this value, and how much does the tool have table have to travel? The table has to travel this much, and during that time the workpiece has to rotate once. Okay. Workpiece has to rotate once during the time that the tool moves by this much. So, suppose the lead is given to us. If it is not given to us, something else must be given to us. Say you will be given something like 32 teeth, then maybe 15 degrees helix angle, all these things. So, first of all, we will be calculating the diameter, pitch diameter of the gear. What will be this equal to? It will be equal to, module will be given, normal module. So, normal module, so let me write down Mn is normal module. Normal module into number of teeth, okay, divided by cos alpha, because in order to accommodate teeth at this angle, the diameter of the pitch diameter of the helix angle is slightly larger than the corresponding what do you call it, spur gear. So, pitch diameter of this helical gear is this much, and if you want to find out the lead pitch diameter, you can use this expression, that this one multiplied by pi and pi d by L is equal to tan alpha. So, we know alpha, so we can put here, and this one it becomes known to us tan 15 degrees, and d has been calculated just now. And therefore, you can easily find out L. Once you find out L, you can divide this by pitch equal to 5 millimeters to find out the number of rotations of the lead screw. Once you get this value, once you get L divided by P, these many rotations enter the gearbox, and the gearbox ratio is not known. That is what we need to find out, ratio of gearbox equal to, say u, a variable, equal to actually output by n input. This is the input. So, this multiplied by this will give you the n output. This one multiplied by the indexing head ratio. So, it reduces the RPM by a factor of 40. This must be equal to 1, and from here we will be able to find out this value. Okay. So, this calculation will tell us what should be the gear ratio for cutting a definite helix angle on the milling machine. So, with this we come to the next part of our discussion, gear generation. Gear generation is much more sophisticated than gear milling, We have already discussed it while discussing gear milling. So, we will now directly go on to some methods of gear generation. Gear hobbing. Okay. What is gear hobbing? Gear hobbing means that just like a worm and worm gear, they are meshing. Okay. Let me just give you the idea in simple words. Just like a worm and worm gear is meshing this way. If you look at it from the top, this is the worm. And this is the worm gear. And this is the worm. What if I did not have the worm gear fully made, but it was simply a cylinder, and the worm is perfectly made of solid, strong and hard and strong material, and this is soft, and I made them go through the motions as if they are fully operational worm and worm gear. The worm will essentially remove those portions of the soft material which do not belong to the worm gear. So, I provide them with motion as if they are worm and worm gear, okay. But this is just a solid cylinder. This is just a solid cylinder, but of soft material. So, the worm will selectively push out all those materials which do not belong to it, but if it is hard, it cannot do it. So, in that case, what we do is from such a worm we remove material, okay, we remove material so that in longitudinal gashes, so that it develops cutting edges. So, you have a threaded element. Ordinarily it has smoothly running helical threads like these, but we remove that here. We remove material here so that it develops cutting edges, it develops cutting edges here. This is a cutting edge it develops, I have lost the figure. Okay. I remove material from this thread so that these threads are discontinuous now, they end up here, and therefore, it develops cutting edges here, sort of. Okay. These are sharp. So, as it is sharp, now it can engage with a hard cylindrical body and remove those materials which do not belong to it and cut it away. But for this, we need to give it certain types of motion. What are these motions? First of all, if I have the cylindrical body, I need to rotate it. So, this is the work piece now, it has to be made into a gear. This is the worm which we were talking of being used as a cutter, and it is given a name called hob. The hob is a worm with cutting edges. So, that also needs to be rotated. So, let us see, we rotate this, and in order to cut from the top to the bottom, in order to cover this whole width, this needs to be moved downwards. So, these are the three main motions that we need to give in gear hobbing. What else? In addition, if you want to cut helical threads, we need to disturb this speed ratio that they would have if they are worm and worm gears. Okay. We disturb this ratio so that the worm, instead of cutting straight down, the cut gets staggered to one side. So, for that we add or subtract an extra rotation to the workpiece. Okay. So, this is what hobbing is all about. What is the characteristic feature of hobbing? Hobbing can cut very accurate gears, provided you are using a say single thread hob. If you have multi-start hob, instead of single start hob, there might be accuracy problems, that is geometric accuracy might suffer. So, here we have shown some figure of the hobbing machine which at the outset will be difficult to understand, but we can get the basic idea from this schematic figure. If you look at this schematic figure, what is to be noticed is that from the motor we derive power. First of all, the hob has to rotate, the blank has to rotate, and the hob has to go down. And we are placing some gearboxes to make the machine very versatile. You can notice there are 4 gearboxes. What is this one for? The speed gearbox or UV is to have higher rotational speed of the hob, okay? Higher cutting speed. If you want higher cutting speed, you can increase the value of UV. If you want different numbers of teeth to be cut, you can change this one. So, we can quickly write UV for changing cutting speed. For example, UV is here in the detailed figure, UV is here. What is UI? UI is the index gearbox, okay, index gearbox for changing number of teeth. If you want to cut a different number of teeth, you use this one for different number of teeth. What is US? For controlling this up down motion, feed, okay, feed gearbox it is called. US is feed gearbox. Last of all, this is for changing the helix. If you want to cut different helices, then only we will use this, otherwise it is disconnected, okay. So, I would like to show you some calculations. Let us see whether we can do it very fast. Yes. For example, suppose I am interested to get this UV designed. What should be the value of UV? Now, where is the hob rotating? The hob is rotating here. So, let me give you some values. I want hob rotation. Hob rotation will define the speed that it develops in its periphery. Hob rotation to be 100 RPM. How can I get that? So, I start from the motor, that is what should be UV so that I get 100 RPM on the hob. So, we can make a calculation this way very fast. I start from the motor 1400, I multiplied by UV, I do not know the value. So, UV multiplied by, it comes out and there is a 1:1 bevel gear, then belt pulley speed ratio is given to be 4/5, then again 1:1, 1:1 etc., all these things. Hob, that is it, 100. So, UV will come out to be 500 divided by 4 into 1400. Let us cut this out and we get UV is equal to 5 divided by, what is this, 4 into 14. So, that means 2856. This should be the ratio of UV. This should be the ratio of UV, 5/56. Okay. Let us see in what way this figure is connected to this one. This is a schematic and this is a detailed one. Do they tally? For example, from the motor it said UV and then you come to the hob. So, from the motor UV and then through all these things you come to the hob. So, this matches. Let us take another connection, like can we find out how UI is placed here? So, UI is placed between blank and the motor. So, from the motor first we will go to UV and then there should be a bifurcation. No bifurcation, here there is a bifurcation. So, this one had gone to the hob and now we are coming in the other path. This is our other path. So, what is this? Sigma. Sigma is this member, it is called a differential. The differential has the advantage that it can add up two inputs and produce one output. Now, why is it put here? It is put here with this idea, if you want to cut spur gears, simply have this input and it produces a fixed output. In that connection, during that time, if you are cutting straight spur gear, do not connect this up. If you are wanting to cut a helical gear, then that extra rotation which we were talking about, it is provided from this side. So, that you have two inputs now and a single output. So, since a differential can do that very nicely, so we have put a differential here. So, differential essentially adds up the input for spur gear cutting and the input for helical gear cutting and produces a common input and common output. Okay. So, at this moment we are not talking about any differential, but we are talking about a particular number of teeth to be produced and how to design UI with that. Generally, when the differential is not connected in any way to the other line, we can take its ratio to be half. This can be proved. Okay. So, for the time being, without proof, please accept that this is going to offer half as a ratio in the kinematic chain. Therefore, we can establish it this way, that let us, if we have to calculate what UI should be, let us say how many number of teeth we want to cut. So, let us say we want to cut 160 teeth. How many what is the speed, what is the characteristic of the hob? Say k is equal to 2, that is, it is 2 start. Then what should be the speed ratio of the hob and blank if they are treated as worm and worm gear? Generally, if you remember, we have already derived that worm gear speed by worm speed is equal to k by z, and that means this is 2 by 160, which is equal to 1 by 80, sorry 1 by 80, and therefore, this speed ratio should be maintained. If we sort of control the speed ratio to be 1 by 80, then we will end up cutting 160 teeth. That is the idea of gear hobbing. Okay. So, let us see how this can be done. Let us travel from the hob, end up in the blank and set this RPM to be 160, and from that solve the value of UI. So, what we do is we start from the hob. Say hob is rotating at n RPM, that is fine. Hob rotates n RPM, and therefore, we go this way, okay, 1:1. We come across this one, and we have already agreed that this is half. So, this is half. So, we are traveling this way. We are coming here, going this way and ending up in the blank. So, multiplied by half, and after that we directly move on to UI. Okay. UI. So, multiply UI, this is not known, this only will be calculated, multiplied by out we go up, and this is having k equal to 2 and z equal to 50, this particular worm and worm gear mechanism just preceding the workpiece. So, this is 2 by 50. This must be equal to how much? This must be equal to, if the hob rotates n times, how much should the job rotate? We know that n worm gear is equal to, is related to the worm this way. Sorry. ZWG. So, this is 2 by 160. So, we can remove NW and keep it here. So, NW, N worm, that is. So, we simply put this value here, N worm multiplied by 2 by 160, and therefore, UI can be solved. N worm cancels out, and therefore, we have 2 and 2 cancelling out, and therefore, UI is equal to 100 by 160. So, this one cancels out, this is 8, no sorry 5 by 8, ui is equal to 5 by 8. Okay. So, since time is short, we have to cover other things also. I will leave this here and give you a text question with the solved answers and upload it, so that you can follow. So, we will directly move on to another subject now. So, this way all the all the gearboxes can be designed, what their values should be. So, now we come to the idea of gear shaping. Gear shaping can be explained in just one sentence. While two gears are rotating, if one of them, so if these two are rotating together, if one is a solid and the other is made to reciprocate, this one will remove all the material it meets on its way, and what will result is the actual gear. So, there is a solid material and this one is a perfectly made gear. They are made to rotate together, that is, you are giving them individually rotations so that they are rotating against each other. This one reciprocates and it removes all the material while they are rotating together. That is it. This is gear shaping. Gear shaping is very accurate, but it is slower than gear hobbing. If you want a gear to be very accurate and if you want it to come out very fast, then you should go for gear hobbing. Gear shaping is slower, but it does not have that problem of number of starts, etc., etc. It is very accurate. Next, gear shaping has a structure of this type. Okay. Let us try to draw the what do you call it, the schematic drawing, since it is not provided here. So, if we notice, this is the motor, this is the way you can read it. Okay, this is my motor. Now, what are my outputs? I am, first of all, as we discussed, the cutter is moving up and down. So, I write cutter. Okay, the cutter is slightly trapezoidal, so that it has cutting edges at the beginning, at the front, but otherwise it is just another gear. So, up and down, up and down, and in order to control this up and down movement, that means to get different speeds, we put here a gearbox. So, UV, the speed gearbox, it controls the speed. Okay. So, from the motor we will connect to the speed gearbox and that connects to the reciprocation. So, that is it, it reciprocates. But the cutter and the workpiece, they are also supposed to roll. So, you have to provide rotation for the workpiece. So, the workpiece is here, I mean cutter and the workpiece. So, this has to rotate as well, and in order to control this rotation, we provide yet another gearbox, and this is called US. We draw the power from here. You might say, why did you suddenly draw it? There is a definite reason which I will be explaining. So, we give it to this one for rotation. So, the workpiece also must be rotating. So, for the workpiece, we draw the power from here and rotate it. While rotating, we place another gearbox, and this one is called the index gearbox. It controls the number of teeth. So, let us quickly have a look. Is this really coming out this way? Workpiece, cutter, cutter. Cutter gets two motions, up and down and rotation. Workpiece gets one rotation, one motion, that is the rotation. Okay. So, that is interesting. So, let us see, does it match with this one? Okay. Speed gearbox. Speed gearbox is here. So, from the motor speed gearbox, yes, it matches, and after that there are some some mechanisms, and this one is rotating, and this, just like those steam engines, it has having a crank connecting rod mechanism, and it moves up and down. That is good. So, it moves up and down. Here there is a bifurcation, the power is taken out here after the speed gearbox. So, after the speed gearbox, the power is taken out and it travels, and this itself is called the feed gearbox, this one. Okay, it passes through the feed gearbox and it goes to the cutter once again, but now to rotate it. Okay, with this one you have bevel gears and worm gear, and now this one, while it is moving up and down, it also rotates. Okay. How does it do it? With a splined shaft. I will be uploading a figure of the spline shaft, so that you can understand, also a figure of the gear shaper in operation. So, after this there is a bifurcation also, and this is the bifurcation, and it comes here and goes into UI and ends up in the workpiece. Now, suppose I set some problems for you. What should be this speed gearbox so that the cutter has 98 strokes per minute? So, I will start from the motor once again, and I will write 1400 multiplied by UV multiplied by, there is a worm gear there. So, K by Z 2 by 20 multiplied by pulley speed ratio 3 by 4. This one itself, one rotation here, one reciprocation here, this itself should be the number of strokes per minute, 98 strokes per minute, and from here UV can be solved. Okay. I leave this to you. Most probably this will come out to be 14 by 15. Please calculate it yourselves. Suppose I also set that the rotation of the cutter per minute, sorry, not per minute, per stroke of the cutter, the rotation of the cutter, which will define how fast they are rolling. If they rotate too fast, then the surface roughness will suffer. So, the rotation of the cutter, suppose I set it to be say 0.25 millimeters per stroke of the cutter, just like feed motion on the lathe per revolution of the job. So, here per stroke of the cutter. If I set this, how are we going to solve it? So, let us start from one stroke of the cutter. So, when it executes one stroke, then when it executes one stroke, then basically then this rotates once. So, we start from here, big pulley rotates once. So, feed gearbox is getting an input RPM of 1, I mean rotation of 1, not RPM. So, US 1:1, 1:1, then it enters K by Z equal to 1 by 50. This one is the number of rotations of the cutter. Per rotation of the cutter executes a circumferential motion of one circumference pi d. So, x rotations will have x into pi d amount of circumferential movement. So, this is the number of rotations of the cutter multiplied by pi d, pi into d is equal to module into number of teeth. So, we write module into number of teeth on the cutter equal to 0.25. This is the millimeters of amount of millimeter movement of the circumference of the cutter per stroke, feed motion. So, suppose I give you ZC equal to 20 and M is equal to 2. So, you will have US into 1 by 50 into pi into 20 into 2 equal to 0.25. Okay. From here US can be calculated. So, I will frame questions, formal questions on gear hobbing and gear shaping and provide it to you, so that you can have a good idea how these machines work. So, that is the end of the 18th lecture. Thank you very much.